¿con quién estoy? Estoy con Carole Mundell. Carole, la verdad que es un privilegio poder hablar con ella. Carole no solamente es la directora de Ciencias de la ESA, sino que además es la presidenta del Consejo Científico del Reino Unido. Así que la verdad es que, Carole, I really want to thank you for your minutes. How are you?
I'm very well. I'm quite excited. I'm a little bit tense. All of the things you would expect the day before a major launch of a huge mission.
I can imagine. Euclid, I mean, I want to understand, this is a fascinating mission. Euclid is not targeting any specific object or sector of the sky. It's more like a cosmological mission. Why so important?
The reason Euclid is so important is because we're trying to answer one of the fundamental physics questions about the nature of the universe. So we think we understand only 5% of the universe, and the other 95%, the so-called dark sector, is unknown. We've seen the consequence of dark matter and dark energy in the measurements that we've made from missions to date, but we don't understand what causes the consequences that we see in our data. And we need to understand whether we have the right laws of physics, or whether we need to formulate new laws of physics, or whether there are new particles and new kinds of phenomena in the universe that we've yet to discover.
So we have these two unknown forces, like a dark matter, dark energy. Actually, I don't know if we should call them dark. They're invisible, right? One, it doesn't interact at all with the electromagnetic spectrum. We only know it because it's gravitational effects. So one, dark matter is like the architecture and providing a structure in the universe, and then we have like dark energy, like pulling everything apart. They're like competing each other. It's crazy.
You're right. I mean, these things, there is a tension between them. There's possibly an interaction between them, depending on the physics theories that you look at. We know that the gravitational attraction that we see, for example, that makes galaxies hold together, so the speed that galaxies rotate at, is too high for the amount of radiating matter that we see. So whatever we look at across the electromagnetic spectrum, from radio waves all the way up to the highest gamma rays, and we add up the census of mass in the universe, we're missing a large component of it. Over 25% of the mass effect in the universe appears not to be in the form of electromagnetic radiation that we can use as a tracer. So that's why we use the word dark. We haven't yet caught light from whatever it is that's causing this deformation in space-time. And then on top of that, Einstein's equations predicted an expanding universe. What we discovered in the late 1990s was that the expansion of the universe due to the Big Bang is not expanding in the way we expect from the laws of physics. In fact, that expansion is accelerated. And so we have no theoretical framework to explain why the expansion of the universe should be speeding up. And that's really what we want to understand. Do we need to adjust our laws of physics? Is there something that we don't understand? And of course, the measurements that we've made to date, they've given us a hint of this, but they have systematics. They're not uniform across different telescopes, across different experiments. So what we're doing with Euclid is controlling on all of those systematics. So we will not just be measuring dark energy and dark matter separately, but also the interplay, as you say, between the force of gravity that pulls things together and the expansion of the universe.
Carole, we launch Euclid is working perfectly. What is, if your number one result that you're waiting? I mean, you've been working on astronomy, astrophysics, you're a physicist. What is it that you want to receive from Euclid? It says, yes, bingo. What is it?
Well, actually, if you ask the cosmologists, they're looking for a single number. So it seems incredible you do all this work and you boil it down to a single number. And that's called the W parameter. And this number really tells us about the balance between the pressure and the energy, the pressure and the density of dark energy. And the number at the moment is calculated from the small surveys that we have is -1. And we want to know whether it's a constant through cosmic time or whether that's changed in time. The reason we care about that is because that's possibly the missing piece of Einstein's general theory of relativity. And famously, he wrote his equations down. There is a constant mathematically, the so-called cosmological constant, and he tussled really with whether he should have that in his equation, whether he shouldn't have it in his equation. And at the time he was doing his maths, he was very uncomfortable apparently about the idea of an expanding universe, and he supposedly wanted to put this constant in to make the universe a steady state universe. So for him it was almost a philosophical as well as a physical question. It comes out of the maths. We can have a constant there, we can set it to 0, or it can have a value, or it can change with time. So the cosmologists want that number. They want to know if that number is constant through time or whether it changes through time, and that will start to give us a sense of why our measurements have shown this accelerated expansion in the universe at this point in time.
Wow. We were discussing a few minutes ago in the press conference about the amount of data that Euclid is going to provide us. And I was listening to you guys, like data centers, the amount of processing that we need. Are we conscious that probably the biggest discoveries are going to be discovered by another generation?
Oh, absolutely.
With the data from years to come?
Yeah. I mean, I think this is what I've seen throughout my career. The computing facilities that we have are never enough to exploit the incredible engineering of the facilities that we build at the time we build them. So the way we do science is we will have a question that we want to answer. That may be testing a prediction from a theory and then really stress testing that theory. We may have an idea and a question that we formulate around that idea. We then speak to our technologists and say, is it possible to do this technologically? There may be existing technology we can adapt. More often than not, we have to invent new technology, new engineering. And we do that, and we engineer it to such incredible quality that the data that those engineering systems then produce for us will open up new windows in the future for new generations to ask new questions of. And the big challenge we have, you mentioned the data centers, we have to be good custodians of those data. So we won't do this experiment and then throw the data away when we get our answer to what W is, for example. And obviously computer architectures change with time. And I see this very much at the European Space Astronomy Centre that I'm head of, just outside Madrid. We have data from missions. I mean, the Hubble Space Telescope, celebrated its 33rd birthday in April. The data that we were taking 33 years ago is very different to the data we have now, but we have to curate it and make sure that we can still mine it. I have young scientists who have come to ESAC on archive fellowships. They've competitively won a fellowship to come and mine our archives and do incredible things with missions that we never designed to do that in the first place. One example was a brilliant young woman who was working with me, not my idea at all. She won an archive fellowship to come to ESAC to use Planck data. Now, our ESA Planck mission was a cosmology mission. It was studying the cosmic microwave background, and she figured out that she could start to do some time domain astrophysics with the archives, and she might be able to look for metallic asteroids, which is incredible, right? We didn't design that mission to do that, but the quality and the beauty of the data, working with the experts at ESAC who can dig a bit more out. So yeah, it's very exciting, but we have to think of future generations.
Actually, we are still working on Cassini data.
Yeah, exactly.
The other day, last week, we discovered phosphorus. It's unbelievable. Carole, thank you so much for your time and for explaining so clearly what Euclid is going to mean for all of us. So thank you so much.
Thank you so much.
And good luck tomorrow.
Thank you. Fingers crossed.
Yes. Gracias, un placer haberlo tenido a Carole, la verdad, toda una eminencia y con un prestigio increíble a nivel internacional y científico, así que ojalá mañana tengamos un exitoso lanzamiento. Gracias.